And she was a professor as well as dean of School of Physical Sciences at JNU. After that, she got into institution building. So she has been the founding director of School of Natural Sciences and Dean of Research and Graduate Studies at Shivnazar University. She was also the second Vice Chancellor of Shivnazar University. And she's also unique in the sense that she has had interest in both experimental as well as theoretical physics. So her research areas include experimental and theoretical quantum optics, laser physics, nonlinear optics, quantum information, quantum measurement, and magneto-optics. And today she is going to tell us about this second quantum revolution, understanding the journey so far. So, Professor Ghosh.
Thank you so much, Pankaj. I wanted to thank Professor Prashant Panigrahi and now you for the kind introduction. Prashant, for inviting me. I've been doing this every year. QIQT is sort of growing from strength to strength. Prashant gave me a couple of instructions and I stick to that. I also have a hard stop at 1. I have another meeting in Delhi. I have to leave for that. So what I plan to do, we are running a little late and I still would like some discussion time. Let's see how it goes. This is just before your lunch hour, so I hope you are with me. So I'm not going to talk about a specific problem and show you the details. What I'm going to do today is give you a bird's eye view of this topic that many experts you'll be hearing from on the details of. So last year, I talked about what is called the first quantum revolution, more or less. It basically talks about, the nomenclature you may or may not agree with, I don't. But that's what people call the first quantum revolution, which enable lasers, transistors, for example, and they're based on rules of quantum mechanics. So in the second quantum revolution, we aim to control quantum systems. It's just not applying it, but controlling it. So quantum technologies today seek to use quantum phenomena in computing, communication, sensing, and metrology. And you go beyond what classical systems can do. Everybody understands that, but this is what is known as the second quantum revolution. Last year, I talked about what is a photon, how do you define coherences in different systems, and then some typical quantum features that you use in these quantum systems. Today, the reason I'm talking about the second quantum revolution is that from last summer to this summer, 2 exciting things happened. Everybody knows about this one, I suppose, in this audience, that 19th April, Union Cabinet of India decided and announced on what we now call National Quantum Mission. A lot of excitement because there's a substantial amount of budget allocated for it. It's supposed to have 4 thematic hubs set up in the country in top academic and national R&D institutes, and they would be on 1, quantum computing, quantum communication, 3rd, quantum sensing and metrology, and 4th, quantum materials and devices. So this is very, very exciting. And one more thing that happened earlier than this in this area is the quantum, the Nobel Prize in the area of entanglement. I mean, for experiments with entangled photons, establishing the violation of Bell inequalities and pioneering quantum information science. So 3 people got it last, end of last year. Alain Aspect, who is a long-time friend of mine, and it's been due for a very long time. John Clauser and Anton Zeilinger, who worked on teleportation a lot. So I'm actually going to start by, a bit of history, because this Nobel Prize, which has long due recognition, reminded me of the work that I've been doing. And it's probably important to go back to the roots of how do you actually create these sources for the quantum resources for which Alain Aspect, for example, got awarded. So this is, class 12 physics. You all know that, but it's a summary for completeness that quantum mechanics, of course, demanded a whole change in philosophy from the determinism of classical physics, when you have concepts of, for example, trajectories. You throw a ball, you know exactly the path it's going to take, provided you know all the forces acting on it. So it is determinism of classical physics. You actually encounter in quantum mechanics predictability, which can at best be probabilistic. So this is not classical statistical mechanics. It's not by choice that you are giving probabilistic description of things that you don't know anything details about. These are in principle unknowable. So there is an intrinsic, in principle, indeterminacy. You're all familiar with uncertainty principle, and that led to a whole lot of conceptual problems. Today, I'll not tell you stories, but again, for completeness, Einstein, of course, dismissed this uncertainty by saying God does not play dice with the universe. I don't know what he meant by God, but for completeness, for this plenary, Einstein believed in mathematical laws of nature. That's very clear. His idea of a God was perhaps someone who formulated the laws and then left the universe alone to evolve according to these laws. And I think that's what we physicists have been trying to believe and work within. So what is quantum entanglement? Again, not in equations, but understanding the concept is, this is what Einstein again called spooky action at a distance. So what happens if two particles are entangled? So you have an entangled pair. What happens to one of the particles in that pair determines what happens to the other particle, as if one particle effectively knows something about the twin instantaneously, even if they're far apart. So this was really, really incredible. And the Nobel Prize recognizes this quantum resource and experiments with it. I'll not go into the details of inequalities. It would take an hour by itself, coming to what is happening today. But essentially, it was John Bell, as you know, who developed a mathematical inequality that states that if there were hidden variables, the correlation between the results of a large number of measurements will never exceed a certain limit. Now, practical experiments by Clauser in 1972 onwards, and then Alain Aspect 1982 onwards, decisively violated Bell inequality and basically proved that the quantum mechanics cannot be replaced by hidden variable theory. All of these things is actually very simple, though you all know, you would see the connection with the phenomenon I'm going to talk about, is the double slit interference, where you assume the source emits light of one color, single frequency, and it's emitting, it's very, very weak a source, so only one photon is there at a time from source to the detector D. In between, you have a screen with tiny holes A and B. So you know the phenomenon of interference. Sometimes light plus light can give you no light, depending on where the detector is positioned. So light plus light, no light is a dark fringe, and light plus light more than twice the light intensity is really what we call the phenomenon of interference. So I'm rushing through this a bit, but you basically know, but it's important to go back to the basics and realize what Feynman had said in the basic lectures on physics, volume 3, that this double slit experiment has in it the heart of quantum mechanics. In reality, it contains the only mystery. We cannot make the mystery go away by explaining how it works. We'll just tell you how it works. In telling you how it works, we'll have told you about the basic peculiarities of all quantum mechanics. So the idea of when I was doing my PhD was, quantum mechanics is that peculiar. Can we actually make use of that peculiarity? And that's how this entire field has come into being. If you're shooting one photon at a time, it appears like a single dot on the screen of the detector, but it has the probability amplitude of going through both hole A and B. So Dirac had given a quantum mechanical explanation, saying that we should think of this single photon as being associated with both paths simultaneously. So there are two indistinguishable paths: source hole A detector, source hole B detector. These two probability amplitudes, is a very strange name, but these two probability amplitudes interfere. If we try to determine with which beam the single photon is associated during the course of our measurement, we would force it into one or the other beams and no interference would occur. So essentially it says something that I'm sure you're familiar with. So there is no reality independent of observers or measurement unlike what you would like to think that there is an objective reality out there, by physics measurements, you are actually extracting information about that reality. There's also no locality, and something that I used to joke about and call it a Sai Baba effect, the extent of the wave function. What if I have talked about a pair, but what if many photons or many atoms are linked in a single wave of light and matter? Now, so there is no locality. You can simultaneously see me in Kolkata and in Delhi and so on and so forth if I were a quantum particle. So if this is really true of quantum mechanics, then what is the use of this? So I'm going to come to that. So let me bring you to the start point of all this, how it happened, because I was deeply involved in that. Dirac, in his famous textbook in 1958, had stated that each photon interferes only with itself. Interference between two different photons never occurs. In the light of the Nobel Prize, I thought I would say that I'm the first one who showed that it's possible to make two photons being emitted by independent sources interfere. So kind of violating Dirac's statement, but the physics Dirac talked about stays true. So I'm going to just spend 1 minute talking about it. So to do these kind of quantum interference, you have to use light in quantum states. That's the kind of states I described last time. Today, I'm just being, I'm ignoring the definitions today. So essentially, the state of the field is not describable as a simple mixture of coherent states. If light is in such a quantum state, you use and you can create those. I worked with resonance fluorescence from single atoms way back. And then what is very well known now is a use of twin photons from down converter. So you create these two photon Fock states. I did the theory of it and then later the experiment. And these are those papers. And I think you can get a better view of it maybe in the popular books that I'm going to mention shortly. So what the result of this experiment, what I predicted in theory was that two photons can never be detected at 2 points separated by a certain value, which is odd number of half interference fringes, despite the fact that one photon can be detected anywhere. So it's again, you use the quantum mechanical interpretation of interference by Dirac. So you say that one photon, when you're detecting two photons, one photon must have come from one arm and the second one from the other, but we cannot tell which came from which. So there are two indistinguishable paths. We have to add the two probability amplitudes corresponding to the two indistinguishable paths, and that interferes destructively at certain pairs of points where you actually have light plus light, no light at all. So really strange effect. And this is the first time that we talked about it, and it became a textbook example. This quantum challenge, this book, I was not really aware of that. It's quite old, but a student of mine showed me when I was in JNU, and it's a thin book. In 3 pages, it describes the experiments I had done, and you can't read it, so let me just read one part of it out. That it talks about that we produced what? A new source from nonlinear optics. So Alain Aspect had perfected his source, which is the calcium cascade, that was done around 1982. And 85 to 87, this is what I did at University of Rochester, using spontaneous parametric down conversion. I had a single UV photon that can fission into 2 infrared photons if it is passed through certain crystals. So photon plus photon interaction is very weak. It doesn't happen, but if you mediate by a material, this is what the trick was. And this book actually called our work as a pioneering work, because it's the first time anybody actually saw such a source of entangled photons. It was actually shown to be true in this experiment. And it went on to say that the experiment I did, not just creating of the source, the experiment was of course a little different than Bell inequality experiments. It was similar to the EPR thought experiment. And you can look that up. It is a very non-local effect that my experiment showed. And this 2 photon interference that I just described cannot simply be described in the terms of interference of 2 independent photons, but must be envisioned as superposition among indistinguishable 2 photon amplitudes. So this is really essentially quantum mechanics, and it's quite remarkable. And it's impossible to understand this classically. This is what the book says. This is also featured in popular science. For example, in this book by Gilda, The Age of Entanglement, I'm sure you have seen. You can just see that it doesn't describe it, but it sort of catches the historical moment of that time, that in 1987, when my PRL got published, that Zeilinger came upon that. He basically said that I have done their experiment, what they were trying to do. Nobody was aware of this kind of a source of entangled photons and this kind of a non-local experiment in interference, spatial interference, that it was possible. So this down conversion turned out to be the ideal source to perform the two-particle interferometry experiment that Zeilinger and company had been seeking. So this is the start point, and then it has been perfected many times over. I'm talking about 1987. That's the first experiment I did. And then typically what it looks like, this picture on top is from my old paper. The second picture, the colored one, I've taken it from Zeilinger's old article. So essentially, photon pairs emitted along the intersections of the cones are entangled in polarization as well. So you can create superposition states containing infinitely many terms. And then many experiments are possible. The splitting of the photon, you can make it efficient by following energy and momentum conservation laws. And that's what the technology has come up, and a lot of things are happening. We continued with this work, this concept, not the same work, of entanglement in future work as well, but today I'm not going to give you the details of any of that. So as everybody here knows, where do you go with this? So it's essentially the overview is that of this quantum parallelism, and you know what I'm talking about when I talk about the second quantum revolution, that you try to control this. So this kind, which is essentially seen in a double slit interferometer, is exploited to construct a quantum computer. Instead of a bit, zeros and ones, you now have a qubit, which is really combinations of zeros and ones. So it's sort of like saying maybes instead of no and yes. So it's infinite information that you can store in no plus yes. Though nobody has seen a dead plus alive cat, but I am not going to repeat the Schrödinger cat paradox, which I'm sure you are aware of. So in macroscopic world, we don't see this, but in the quantum private world, it's possible to create these kind of parallel worlds come together. So how do you produce, observe, and make use of such powerful information-rich states? And that's really is the key question. That's what this book calls Quantum Challenge. And what is the quantum challenge really? That quantum mechanics shows up in small enclaves within the classical macro world, right? So it's not necessarily based on size, the other parameters. I'm not giving you the exact details, but the idea that all of us are familiar with, the behavior of individual constituents is described by quantum mechanics, but the classical macro world doesn't seem to be following that. Why? Because as was, I think, Shubhashish was talking about a bit, I did not hear his first time, but what he did with me at JNU, for example, was looking into the fact that these quantum systems are rarely isolated and they interact with their environment. And when they interact with their environment, they lose their peculiar quantum character. So it's similar to the flow of information he was talking about from your system to the environment having a very large degree of freedom. The information does come back, but after a very long time scale. So the central question in quantum physics is also the mechanism of transition between the quantum and the classical world. Is there a door that you open from the macro classical world to go to the quantum world or vice versa? So what is it that dictating this transition? So the challenge is, again, a third aspect, I'll show you a summary of that, is that to make a measurement, you need to keep a quantum system isolated for long enough. That's not enough. You also, measurement affects its state. So you have to probe it so delicately that the measurement leaves the system's quantum nature intact. This was known even to Schrödinger in 1952 or around that time, and he called it post-mortem physics because you are destroying the object under investigation. So observing such fragile quantum effects and then making use of a system's quantum nature are tough and challenging tasks, right? So I think because of these two aspects that we talked about. Last year, I think I mentioned this briefly, in end of March last year, this article came out in MIT Technology Review, article by Shankar Das Sharma. Most of you probably is familiar with his work. And the title of the article was Quantum Computing has a Hype Problem. According to this article, what is the main issue is what I just talked about, that quantum states disappear, and that's called decoherence. They decohere in the presence of environmental noise, and error corrections are difficult, right? So till today, this is really the main issue, because quantum computation relies on entanglement of large quantum states to perform efficient calculations. So such states, if they're large, they will interact with the environment. The nature of the interaction and the time scale over which it acts are critical inputs to your, the model, the scheme of quantum information processing. So there are two things that I've already talked about: the problem of damping and associated dephasing in quantum systems, and time irreversible outcome of a measurement. So even today, the question is, how well do we understand the process of loss of coherence and emergence of classicality? The reason I'm mentioning this, that this is really an important issue for second quantum revolution. If you wish to control something, you need to first understand it. And as is being said, my throat is gone. Quantum error correction is the single most important technology for the future of quantum computing. It's because of this reason. Again, I'll not give you the details of it. The series of papers you can actually find. But basic physics of this, as you probably have guessed already from the talks you have had exposure to, is that the system is coupled to its environment. So energy may irreversibly be transferred from the system to the environment. That's what you call dissipation. The fluctuating force exerted by the environment on the system causes fluctuations of the degree of freedom of the system, for example, as you see in Brownian motion. Now, these two occur for both classical and quantum systems. There is a third thing that happens in quantum systems. As the system and environmental degrees of freedom get entangled, coherent superposition of quantum states may get destroyed, and that's what we call decoherence. So let me give you an example of the third one. But before that, as I have been saying, this process of decoherence sort of comes up in 3 or 4 physics problems. So one is what I'm discussing, quantum computing and quantum information. I hope everybody gets the idea clear. Is basically what is determining the time to perform elementary unitary transformations involving the qubits, because this time to do this, these quantum dynamics should be well within the quantum coherence time. Otherwise, the system is no longer a quantum system. It also appears in quantum measurement problem, like I just pointed out, and I'm going to give you an example of that shortly, just to give you an example. It's a toy example. By the way, I just saw that Physics Today is organizing, they have this editor series webinar. End of this month is on quantum measurement and why it's a problem, if you're interested. So this is a problem that has plagued physicists quite a bit. As I just mentioned, the third issue may be explanation of the emergence of the classical world from quantum mechanics. That also you can actually explain through quantum dynamics by the process of decoherence. So it's not going out of quantum dynamics, it's within quantum dynamics, bringing in elements that are already there, part of the quantum system, to explain so-called classical behavior. The fourth one is a very interesting one. It's probably you're aware of today. I don't have the time to talk about it. Arrows of time problem. That means why does time never go backward? Why time is irreversible? you get born and then you die, you cannot go the reverse way. This, of course, the entire belief of causality rests on this, but decoherence also explains to you the apparent irreversibility of time. I'll not get into that. This is, I have called an aside, but each of these four occupy a lot of research area, research output in physics. To give you an example of what decoherence is, let's take a very simple system of spin up and down. And let's say the detector is also spin up and down. And so you can create the density matrix of this combined system of system plus this detector. And in the basis that you choose up and down, the density matrix takes a simple form. The diagonals have mod A square and mod B square. Those are the probabilities of being up, probabilities of being down. But the ones that are in blue, the off-diagonal terms, they are a little funny to interpret. There's nothing funny about them in quantum mechanics, but these are the ones that correspond to superpositions of macroscopically distinct outcomes, up and down, and they are mixed up. So these are classically unacceptable and essentially quantum. So these blue terms are the ones that are troublesome in quantum mechanics, and that's the resource that we plan to use. Now, so from that pure density matrix, you actually go to a reduced mixed density matrix. The reduction mechanism is not taught in standard quantum mechanics textbooks. You just say that there is a reduction mechanism by which you just put those off-diagonal elements to zero. Now, this is then once you have just the diagonal elements mod A square and mod B square, they're easily interpretable like classical probabilities. Of course, a second reduction happens, but that's uninteresting. That's the sort of classical probability distribution collapsing. You have that in statistical mechanics, classical type. So that is not something that is of importance, but the red question mark that you see there is really asking what is the dynamics of rho pure to go to this diagonal reduced density matrix. And that's what the decoherence thing is all about. With my student Anu Venugopalan and Shubhashish Banerjee, who you just heard, a series of things we probe peculiar systems to understand these dynamics of open quantum systems. The reason I'm mentioning these old papers today is that it's still not understood completely for the systems of relevance. And I think to control decoherence completely for large qubit systems, which is necessary for a quantum mechanics, quantum computing, to yield results that is of interest and be efficient, you need to actually do the same thing. So to do that, what are the questions? I'll not give you examples of this right now, but this decoherence noise, as we call it, may arise in a quantum gate and or within a measurement and or in the preparation of the initial qubits, etc., etc. So the questions you need to ask are, how does decoherence evolve in time? Because the collapse is not instantaneous. There is a time involved in that decoherence time. And if you are smart, you would do all your operations within that time so that decoherence doesn't set in. How does decoherence affect n-qubit entanglement? How does it depend on n? That's what I meant. And how can decoherence be controlled and or tested experimentally? So I think these are open problems even today. There's a lot of work we had done, and I showed you you can look them up and probably we can discuss that later. Now I go back, I start asking for elements of the quantum computing system, and that sort of takes us back to Sarja Roche's Nobel Prize in 2012, so it's more than 10 years back. And the citation of the Nobel Committee was nice because it says for groundbreaking experimental methods that enable measuring and manipulation of individual quantum systems. So individual quantum systems. In spite of decoherence, there are experimental methods that enable you to measure and manipulate individual quantum systems, and they got perfected by Sarja Roche's lab in Paris and Dave Weinlein in Boulder, Colorado. Today, again, I'm going to give you an overall perspective, not getting to the details of it. I've talked about them in the context of our work and other times. But in this plenary, I think I'll just give you bird's eye view. Now, my bias, of course, is to work with optical systems. They're not the only ones. I'll give you a summary towards the end. So the ultimate goal is to make individual light particles or photons interact with one another so that photons become entangled. And as I have already mentioned, you know that Maxwell equations are also linear. Photon plus photon interaction never happens. But if you confine photons in a particular material long enough to enhance the interaction, then you see these strange behaviors and exciting outputs like what we did for spontaneous parametric down conversion. So, and quantum information encoded in light pulses is preserved. It can form the basis of quantum memory. And I'm going to spend some time talking about some work of ours and an interesting phenomenon, which today I'll not give you the details of, but I think you would find other talks where I've given the details. The phenomenon I'm going to mention is called electromagnetically induced transparency, or EIT. As the name suggests, it's about cancellation of absorption, even on resonance. So a resonant light may transmit through a medium. If I use a control laser in the process of EIT, otherwise, for a resonant light, medium would appear opaque. Nothing would go through. So that's really an induced transparency. And the nice thing about optics is that nothing gets changed permanently. So when you apply a control laser, I'm going to describe that in that cartoon shortly, then this effect persists. The moment you turn the control laser off, the material goes back to the normal behavior. So what is it all about? If you think of a laser with the red frequency omega falling on a material whose two energy levels I'm considering shown to be separated by omega naught. And these are the relevant transition, only the relevant transition is being shown. And the detuning between your incident laser and the energy of separation of the two levels is delta. So a very simple thing in Jackson to all electromagnetic theory books, you see these curves for absorption versus dispersion spectrum. So it's frequency on the x-axis. A y-axis absorption is maximum when delta is 0. That means when the incident light resonates with the frequency of the two levels, the population gets lifted actually. So light doesn't come out, it gets absorbed, and absorption peaks. And there is by Kramer-Kronig relation, you have a causal relationship of absorption with dispersion. They are given by the real and the imaginary parts of your susceptibility. So imaginary part absorption, real part dispersion, and the dispersion shows a really negative slope right at delta equal to 0. When detuning is 0, then dispersion has a negative slope. Now this gets dramatically modified if I apply a second laser using a third level as shown. Where there's a peak of absorption, now you have a dip in absorption. That means a transparency window appears around delta equal to 0. And similarly, the dispersion curve, where there is a negative slope of dispersion, now there is a very steep positive slope around delta equal to 0. So this extreme positive dispersion in this window leads to what people call slow light. What is slow light? Any material, light goes through it. This is again high school physics. Light passes through it, it gets slowed down, and the factor of the slowing down you call refractive index, right? So if I call the group velocity of light as V sub G, then the dispersion relationship basically tells you that it would be C divided by Ng, the first order dispersion. That Ng is the group index, which is greater than 1. So the group velocity inside the material is always less than C. C is the free space speed. Now, that's nothing surprising, but Ng could be of the order of 1.5, 1.3. In semiconductors, maybe 6. But now we can talk about maybe Ng of the order of 10 to the power 6, 10 to the power 7, Therefore, the group velocity becomes really small. So what essentially like cycling through a material where you have EIT. And not only you have transmission, you also have this extreme positive dispersion and slow light. And this is what is very exciting. And the natural question you'll ask is, if I can slow it down, can I stop it to create a memory inside this material? So, again, I'll not give you the full details, but the phenomenon is really, again, quantum interference. And in quantum interference, you have two fundamental quantum ideas. One is of probabilistic interpretation, and second is addition of probability amplitudes for indistinguishable paths. Both these fundamentally quantum ideas show up in interference. And in physics of EIT, one way of understanding is also understanding that it as an interference phenomenon. So the probe laser that I showed as omega 0 under resonance condition would actually help lift the population up there. But now you have a very strong coupling laser on the third level, on the second arm of this lambda. So for the population which is shown like a blob, it's just a cartoon, don't take it literally. So it has multiple routes of excitation. So absorption of the probe can be via two channels. One is a direct one, that it goes from lower level B to upper level A, and an indirect one mediated by the coupling laser, which is B to A to C to A. These two paths, the routes, interfere, and quantum interference of these probability amplitudes lead to cancellation of probe absorption along from B. So B to A, nothing gets lifted, though the laser is actually on resonance to the probe transition. So this is the physics of EIT. Again, there are two paths, and the two path probabilities, probability amplitudes interfere. To have this interference, every time you talk about it, be it double slit or here, you really have to talk about a coherence time. And in this case, the coherence lifetime is really the Raman coherence lifetime of the two lower levels, B and C, as shown here. And that what limits the operations that you want to do. So this quantum effect of transparency will be valid only during the Raman coherence time, which is shown here schematically. So really, it's a remarkable phenomenon. And the lower state B is called the dark state in this case, because it's in light, but poor thing doesn't see any light. And this is really a capital lambda system, as we call it, because the two transitions look like capital lambda. So essentially, what exactly do you need to do if you want to practice this? You have to control the behavior of an atomic medium. That's your goal. The control in the second quantum revolution is what we are trying to do. So you control the behavior of an atomic medium to switch between transparency and absorption at multiple frequencies. You can create logic gates, switch on off kind. And so again, the process relies on quantum interference. The first trick for anybody to do this is to be able to select a simple usable atomic level. And that's what we had done, is to really see this magnificent quantum coherence effect. But it's done not in small systems. It's done actually in bulk systems and not at low temperature, at room temperature. That's what I did way back, but I would not give you the details of it. Just to tell you, it's possible to do this. And we did it with room temperature metastable helium. In the French collaboration, I had a long-standing collaboration with Fabian Bretneka, and this helium experiment was actually the specialty of Fabian Goldfarb in Orsay. We had funding, and then it came out as we got graded excellent both times, and it got featured as a very, very successful research collaboration. So there's a lot of references of our work. where we have talked about EIT, adiabatic transfer and slow light. What is adiabatic transfer? Essentially, okay, some of the thing, I think I can skip all of this. Before I go to adiabatic transfer, let me say an interesting thing, which I talked about some time back in another forum, but I was saying that Vg, the group velocity of light inside the material, is C by Ng. If Ng is much larger than 1, then you have slow light because your Vg is much smaller than C. So is it possible by manipulating the slope where exactly you operate in the detuned system to create fast light where Ng is less than 1? So Vg would be greater than C, or even backward light, which we did, where Vg could be negative, Ng would be negative. So this is really very counterintuitive, and you would think that such fast light or superluminal propagation is not possible because that would violate causality. What requires a lot more work and rewriting of textbooks is to say that group velocity actually does not carry information. Information propagation is better described by some discontinuous front velocities when you turn on the coding. And so therefore, group velocity becoming greater than C does not violate Einstein's causality. I'll not get into the details of it today, but this is something you can look up. We actually did some experiments, and here is some sample of this, where we have actually shown what I call negative light. So before the light enters the medium, it has actually come out already. So very peculiar things. The words fail you because this description, which is based on first order, cutting off the dispersion terms to only first order derivatives, that description fails when you have such abrupt, discontinuous coding of information. So I think we understand that, but it came quite as a shock to everybody when we said that Vg could be greater than C and Vg in fact could be negative. So, but in experiments, you can actually neatly show that. I'll not get into this part as well. I have marked it as an aside. Another student of mine worked extensively on coherent population oscillation, CPO as it's called. And this is another way of doing the same thing that I was talking about, creating resonances, creating transmission resonances by playing with lasers. And we worked on a tripod system. It's kind of, it's a 4-level like a double EIT. And, you can actually solve this and try to figure it out what exactly happens. This system actually works like a polarization dependent switch. So in the presence of a small magnetic field, and so it's extremely useful. Another example. I mentioned briefly the adiabatic process. So I think the question that, again, this particular paper, I'll not get into this. So let me move from here. There is a PRL in 2017. We talked about light storage, again, a memory using CPO, the coherent population oscillation I was talking about. And so we tried to give it a model by calling it a populariton quantity. It's a mixture of populations and fields, and like you have dark state polariton or EIT used by Lukin and company. So anyway, so these are models that one can take a look at it. Here is a summary of the physics concept of what I'm talking about. That can we actually stop and restart light? Can not just slow it light, but stop it so that you can store information with whatever has come into the light. The basic physics, is that photons with zero rest mass cannot, of course, be stopped. But if I have light plus matter interaction, then you create what we call rest photons, like those polaritons I mentioned. And these are essentially joint oscillations of light and collective atomic dipoles. And these would have non-zero rest mass because they're dressed by the field. And so you can, in a sense, have zero velocity in a particular frame of reference, in a moving frame of reference, that is in a moving medium. So people have been talking about self-stopping. Those are different things. This is not what I was talking about. Idea is if you can actually stop light, which is extremely difficult to do, but with these kind of light matter nonlinear interactions, you can actually stop the light. Then if the incoming light was carrying information that were coded by changes or modulations of its either frequency or amplitude or phase or all, then when the light stops, that information gets stored in collective atomic excitations, just like information is stored in the electronic memory of a computer. So the idea is to restart, to access the information, the control laser needs to be turned on, and out comes the original light. So this is the peculiarity of this, that the information that is stored in the light, you don't know it exactly. So you're trying to retrieve information that you do not know, because the moment you know, it no longer stays as a quantum information, right? It becomes a classical information, one or the other. So that's really is the crazy thing in here. So quantum memory would essentially mean a flying qubit becoming a stationary qubit, maybe in an atomic system, so a different form, and then vice versa. And there are storage and retrieval protocols based on EIT. I'll give you just the update as of last year, but that these have been realized in warm atomic cells like room temperature cesium. I talked about helium, but better results in cesium. I'm going to give you that reference shortly. And in cold atoms and solid systems as well, it has been applied to store and release single photon, squeeze state, entangled photon pairs, multipartite entangled states of optical modes. And you can see a review last year's, which, it's a pretty good one, talks about the IT quantum memory for non-classical states of light. That's the information you're storing. And there's a new one that I saw in Nature Communications last May that also talks about sort of 95 degrees rubidium atomic cell, cavity enhanced quantum memory. So a lot of work is going on and nobody has the final answer yet. The best results probably we have seen, and that's what gives us hope for prospects of this, is a room temperature cesium cell that was used in the Weizmann Institute of Science. It's a little old Nature Communication paper that has come out, and that showed a long storage time of 1 second at high atomic densities. So it's not bad at all. High atomic densities at room temperature, you are worried about collisions destroying your coherence time. But in this case, the idea was that the spin exchange collisions were kind of outside your system, and they were avoided completely. That led to this long storage time of about 1 second, even with high atomic densities. So remarkable paper, and a lot more work needs to be done in this. So what exactly are we looking at? We talk about networks. In the classical information network, the WWW, you use the bits for the information to flow through the network. It gets processed and modulated by electronic circuits and chips and transmitted by light pulses to move the information through the network, right? So this is before second quantum revolution. Now, what we are talking about is what Kimball called way back quantum internet, is a quantum information network that will process and store quantum information through quantum bits or qubits in a quantum network. There is thus a potential advantage of perfectly secure data transmission, and that is the secure data transmission is one of the most important features required for quantum internet connectivity and access, right? And that's the fear. What I just talked about is really photonic channels where you, through light, you send your quantum information, and it's appropriate over distance because photons travel fast and they have weak interaction with the environment, and that's the plus point. But photons are difficult to store as memory, as I pointed out, zero rest mass and so on and so forth. So photonic channels are combined with atomic nodes. These can serve as good quantum memories because they're difficult to transport over distance. So essentially, we are talking about an atom photon network as our quantum information system. And naturally, you have to be sensitive to the second important problem that I'm talking about is information transfer problem. how do you transfer information from the photonic channel without destroying it, without reading it, to the atomic nodes, and then retrieve it at will from atomic nodes back to the photonic channel, again, not knowing what that information is. So everybody knows this process of transfer has to happen at a slow rate. And that's why it's adiabatically done. How slow is slow? What is the impact of spontaneous decay, et cetera, that you cannot avoid? We actually probed that, and there's a lot more work that needs to be done. So in the last 5 minutes, all I want to do is to tell you, give you an update. The experts probably know already, but it's important to touch upon one aspect of quantum information processing, the way it's happening. It's out from the academic domain to the market. And I'm going to give you some references on that. So far what we know, and this is a summary, is that real systems are based on either the oldest are trapped ions. That's the first qubit that was prepared by Dave Weinlein's group in 1995, Chris Monroe and Felix, and this was done in Boulder, Colorado. Then there's a very strong candidate of solid state superconducting circuits, and both Google and IBM are working on it. Until last year, October, IBM's Eagle processor, which was 127 qubit, was the most powerful one. IBM has been scaling up. So we had the till 2021, we had the 127 qubit processor. By 9th November, the Eagle processor got beaten by a 433 qubit processor. You must have seen the news. The plan is this year to have a 1,100 qubit processor, next year 1,300, and so on and so forth. By 2025, 4,000 qubit processor should be there. Now, of course, I'm just giving you the number of qubits. But again, let me stress, and this is what you get from newspapers or journals, the number of qubits is one part of the very large and complex puzzle. What is important, of course, how to create longer coherence times and how to reduce noise. These are as important, and those are the points that I talked about in my talk today. So IBM Real Systems, they're scaling up this IBM's quantum mainframe. Probably you know it's called Quantum System 2, and this is to be launched end of this year. So the plan is that this will house multiple quantum processors and integrate them into a single system with high-speed communication links and so on and so forth. So they are working on it. Google quantum processors, the group is called Quantum AI. And in 2019, Google claimed it has passed a milestone known as quantum supremacy when its Sycamore machine executed a calculation in 200 seconds that would have taken a conventional supercomputer 10,000 years to complete. Anyway, that's history. This year, fresh from the oven, in February, there was a Nature paper. So even Google is publishing in Nature, Google Quantum AI. It's a collaboration. So it's a major milestone. They demonstrated that a system using error correcting code can detect and fix errors without affecting the information. So there's a summary that also came out in the same Nature issue towards quantum computers that are robust to errors. I don't think we have seen the end of this, but it's no doubt a major milestone in what they have seen. So this is out there in that. So I talked about ions and I talked about superconducting bits, but the most important real system that is now catching our attention is atomic. So quantum processors that use neutral atoms, and I prepared you for that by talking about EIT and so on and so forth, because these are produced independently by two groups. Again, last year, April, Harvard and Wisconsin-Madison, probably you have read that in back-to-back Nature papers. And the result is a milestone because atomic quantum computers will be easier to scale up than the two earlier technologies because they're neutral. So decoherence effects, So I'm not just talking about how to increase the number of qubits. I'm talking about how to actually understand decoherence and control it. So atomic systems, probably you would have a better chance to do that. So the experiments look extremely clumsy, a typical photo from the Wisconsin-Madison paper. Other advantages have happened. I'll not get into the details at all of quantum teleportation, etc., etc. So the dream is that a future quantum internet powered by such quantum teleportation could provide a new kind of encryption that is theoretically unbreakable. So look that up and we can talk later. A lot of work going on also probing what is called hybrid computing. So what's the right combination of pure quantum, quantum inspired, and classical computing? He also talks about what we call digital quantum computing and analog quantum computing. Maybe I have a slide on that. So different approaches for different applications. That's what seems like the future would be. So analog quantum model or quantum annealing, for example, again, I'll give you a reference on that. And versus, for example, universal quantum gate model, which has been around for some time. So Microsoft's approach is called topological qubit method, and that uses that universal quantum gate model for mass production of qubits. And D-Wave Systems, I'm going to mention them, it's a startup that built the first commercial hardware solution for quantum annealing. Now, quantum annealing is something that you can read up, the Nature paper that just came out. It uses quantum physics, that is quantum fluctuations instead of thermal fluctuations, to optimize low energy states of a problem, and therefore the optimal or near optimal combination of elements. So I think there's a lot of activity happening right now as I speak, and something that's not explored very well, but it's something that I'm putting as an aside. I'll not discuss this. Photonic neuromorphic computing to mimic neurons and synapses, emulating the human brain to boost the prevalent computing capability. Some people are active in this as well. I want to give you some idea, I end it with this, one more slide after this, is that there's startups as we talk this year. There have been some that closed down, but I'll give you some fascinating ones according to me. IonQ is the first one that, the same group in Maryland I talked about. Ion, you can make out who are the people, Divine Line student, etc. Then Zapata Computing, again in the US, this came from Harvard group, and they are developing quantum software with real world use cases across pharma, engineering, finance, and more. Pascal is a very interesting one. It's a French one. It started late 2019, and they're manufacturing quantum processors required by the most advanced quantum computers in the world. So imagine youngsters putting up this startup, which will now manufacture quantum processors and is available in the market. Another interesting one for me is based in Canada, D-Wave Systems. They had a large collaboration with Boston people, came up with this Nature, which has just come out, 19th April issue. And this is what I was just talking about, quantum annealing, quantum critical dynamics in a 5,000 qubit programmable spin glass. So this is an analog system, and it's remarkable. You can look them up and see what these quantum computing startups are doing. How are they making them practical and usable? I end with just a glimpse of somebody had asked me, how do you program quantum computers? It's actually, there are many libraries available. The language is the same old thing that you know already, but I think libraries have been created for you to use, and most of them have pretty well documentation. QIQT is the Quantum Information Science Kit by IBM. You can look that up. CERT is by Google. It's not very well documented, but there's a new version that has come out. That's the website, the new website. There's Forest, there's Project Q, there is Quantum Development Kit, and so on and so forth. So you can use their quantum computers and their open softwares, so you can actually do this and learn how they have done it, and they're used in Python or JavaScript and so on and so forth. So I'll end today like this. I really have to leave in the next 2 minutes, but the moral of the story is in physics, the evolution happens when theory and experiment go hand in hand, and that lead to applications as robust as this quantum information burst that we are seeing. And scientific methodology would continue. It's not like one day we'll solve all problems and we'll all become jobless. So Scientific methodology, therefore, is important to maintain what defines the scientific methods from what I would call non-science. So welcome to that journey, and thank you very much for listening to me carefully this afternoon. Thank you.
Thank you very much, Professor Ghosh, for describing to us the second quantum revolution, and especially the challenges that are being faced by this revolution. Also, thanks for telling us a bit of history about this parametric down conversion, how to get this entangled photon. I think a lot of people didn't know it.
Thank you.
So actually, so I don't know if you have any time to take any questions. You were saying you are in a hurry.
I have to leave, actually. I have a meeting in Delhi. I have to leave right away. But
Sure.
I can take one question. Traffic is bad as it is.
Okay. So anyway,
but definitely a very fast speed.
Okay. Any quick question? Because Professor Ghosh has to leave.
I hope you got the flavor and you got a little bit of glimpse of history where it started.
Yeah.
Hello.
History is always interesting. Any quick question, please?
Very quickly.
Hello.
Yes, please.
I have a confusion the word in probability amplitude and how the probability amplitude is connected. Both are connected, and how can we understand it?
Very good. This is actually very basic quantum mechanics. I wish I had a board to teach you. This is very simple, actually. In quantum mechanics, like the wave function, is not really a physical quantity. When you take the mod square of the wave function, you get the probability of that particular state to happen, right? If the wave function describes a particular state. So the mod square of that gives you the physical probability. The square root of that, for the lack of any good English, our forefathers have been calling it probability amplitude. So mod square of that gives you the probability. So if I have two indistinguishable paths, with each path you associate a wave function. You have a probability amplitude of going through it. So I'm not using probability because probabilities are like intensity of light. They don't have any phase. They don't interfere. So when light plus light gives you no light, you realize that what you are adding is not light intensity plus light intensity, because two positive definite quantities can never give you zero. 0 plus 0 would give you 0, but positive definite quantities, if you add them, can never give you 0. So essentially, it says that superposition happens not at the level of intensity, but at a lower level which we can't see, which sometimes you would call the electric field. But again, that's another concept that is debatable. So essentially, that is the concept. The phase in quantum mechanics is the most important part, which is not there in our day-to-day macro world, and that's the problem. Okay, so probability amplitude is a bad name associated with the square root of that probability for individual events to happen.
Okay.
Yeah.
So I think because time is running out, and Professor